As we've promised in previous video, now we will try to find a process to extract regular patterns in Riemann Zeta function, and filter out the irregularities. Hopefully we can get a bigger picture on how the Riemann Zeta function will behave at high imaginary part, which is the focus of Riemann's hypothesis. From previous video, we've learned about domain extension of zeta function using functional equation, which in turn determines the positions of non-trivial zeros. Riemann hypothesis predicts that all non-trivial zeros of zeta function lie on the critical line, with real part is a half. Every point on the critical line has a special property, it's identical with its own reflection about the critical line. Let's compare zeta of s and zeta of 1 minus s conjugate by subtracting them and plot the result. When the difference is plotted, the curve is hard to comprehend. But when logarithmic function is applied to that difference, a simpler pattern shows up. Its shape suggests that it shall be called y function. Let's zoom in the plot around the critical strip. This is the plot when the division is used instead of subtraction. The complex logarithm of a complex number is calculated as natural logarithm of the magnitude of its input, plus I times the argument of its input. The plots are symmetrical about the critical line. Let's shift the plot to the left by a half, using s equals a half plus d. Let's observe how the plots are evolving from lower to higher imaginary part, starting with 0i. Let's zoom out to see the bigger picture. Let's continue to higher imaginary part. Let's call the left curve y function, and the right curve s function, based on the shapes of their real part. The shapes of real part don't seem to change much with higher imaginary input, only the slopes get higher, and the curves get closer to straight lines. The imaginary part also changes with lower frequency. Let's zoom in the plot around the critical strip again. Now, instead of plotting along the real axis at constant imaginary part, let's plot along the imaginary axis at constant equal distance from the critical line. A bit of asymmetry from the critical line produces spikes to the smooth curve from symmetrical formula. The direction of the spike depends on the difference of distance from the critical line. The spikes points out the positions of non-trivial zeros of zeta function. Let's ignore the imaginary part for a moment, since we are trying to extract regular patterns in zeta function. The smoothness of symmetrical ratio extends to higher imaginary part, and it doesn't seem to have any apparent irregularity. The curve can be approximated by a logarithmic function as shown here. The orange curve is overlaid as imaginary values on the complex plane. The constants were chosen through trial and error, and those curves seem to fit well with each other. The curve fitting function is then subtracted from the s function. The difference gets smaller with higher imaginary part. It indicates that y function is linearly correlated to the distance of its input from the critical line. What we've got from here is that zeta function has more regular behavior with higher imaginary part, in contrast with expectation of those who think that Riemann hypothesis is likely false. In the next video, we will explore further the zeta function and its variations, and try to find regular patterns that can be used to prove Riemann hypothesis.